What's up, guys? We are Team Dudes of Plenty. Team Dudes of Plenty consists of 4 dudes working tirelessly on one mission. And that mission is to construct a quadrular hardware platform to be able to conduct rescue missions in the case of nuclear power plant emergency. My name is Sam. I'm here to talk to you about some of the team philosophy that we have incorporated in the design of our drone. We value safety. Safety is our topmost priority. We think safety is very sexy. And we enforced and try to maintain a zero crash policy. So far we've done it, and we're proud to announce that we're going to continue to work tirelessly to maintain the zero crash policy. And to be able to achieve this zero crash policy, we focus on 2 aspects of our drone. The first aspect is the hardware side. When we were building the drone, meticulous thoughts and careful considerations are placed into details of where the hardware should go and how the wiring should be arranged to make sure there's going to be less hardware failures when we test our algorithms. Secondly, we test our algorithms and methods in simulation environment first. We establish a simulation environment where we're able to see the performance in simulation before we deploy onto the real drone. By doing those 2 things, we are able to combine the best built hardware with robust software, and therefore the hardware failures will occur less frequent, and we can trust our hardware once our software is working as expected. Less crashes to us means more success in our future challenges. Now I'm ready to pass it on to the rest of the teammates to talk about some of the details that went into the execution of our drone platform.
There are 4 major value propositions that makes our drone design compelling. First, it is highly maneuverable. Given its small size, it can easily navigate through cluttered indoor environments. The 3 degrees of freedom movement allows it to reach many areas not accessible by ground robots. The autonomous capability of our UAVs improve workplace safety and productivity, substituting on-site personnel and trained pilots. It also makes the deployment of a fleet of drones possible, enabling the exploration of large areas quickly. Our design is also highly versatile. With a variety of sensor and localization modalities, it can operate in both indoor and outdoor environments for varying payloads and purposes. Given the flexibility of add-on modules, such as GPS and barometric sensors, autonomous drones can be valuable across many industries. We can group them into 3 major types of applications. First, it can be used to perform emergency and routine inspections of hard-to-reach and/or unsafe locations, such as power line infrastructure check, hostage search and rescue, battlefield surveillance, warehouse stockpile inspection, as well as agricultural pest monitoring and detection. Secondly, in transportation, autonomous drones can be used for short distance, lightweight package delivery in dense cities and across difficult to traverse terrains. Lastly, drones can be used for entertainment purposes. Applications range from swarm performances to photography and 3D reconstruction.
With our emphasis on safety, it was necessary to invest heavily in software infrastructure to enhance our development process. We utilize Gazebo for software-in-the-loop testing that accurately simulates the drone's characteristics, allowing for easy transfer from simulation to the physical drone, as well as to allow rapid development and extensive testing before we even load the code on the drone. We use Docker so we can utilize software not typically found on outdated hardware, as well as develop software on any device and transfer effortlessly. We use RViz to get a better estimate of how the drone experiences the world, and to get a better idea of how to improve our algorithms, and so that the drone can operate effectively.
Here is the hardware we use for the drone. We use a Pixhawk 4 Mini as the flight controller, the FrSky Archer R4 receiver for radio communication, RotorGeek's HP brushless motors, SplitX ESC36S as electronic speed controllers for the motors, and an Intel RealSense T265 depth camera for object detection and visual odometry. Underneath the drone we have the TerraRanger EVO60 as a range sensor for flight stability, NVIDIA Jetson Nano for computation and communication with the Pixhawk, and a LiPo battery to power the whole drone. Here are our drone solutions developed to date. Our drones use visual inertial odometry to stabilize its flight. We chose to use VIO because the code is well documented and previous drone engineers have demonstrated it is very effective in stabilizing the drone. When in position flight mode, the drone is capable of stable sustained stationary flight in the X, Y, and Z directions and will counteract disturbances. Off-board mode is an autonomous flight mode that allows the drone to be controlled by a program, and software commands like launch, test, land, and abort can change the drone's flight modes autonomously. We chose to use a VIO to stabilize the drone's movement in the X and Y directions, and the TerraRanger EVO60 LiDAR altimeter sensor to stabilize the Z direction. We tried stabilizing the Z direction with VIO, but we found that using the TerraRanger was more effective in our tests. The hover is extremely stable in the X and Y directions with a very minor deviation in the Z direction due to the integration of the TerraRanger. We created a program that can be run using the test command in off-board mode that allows the drone to hover at a particular waypoint above the ground by switching to the position flight mode. Our drones are able to hover for 30 seconds guaranteed, but they may be able to hover up to 1 minute continuously without recharging. Here are results for Challenge 2. As you can see, there is around a 0.05 meter deviation in both the X and Y directions, and around a 0.02 radian deviation in the yaw over a 30-second period. Our drones are capable of waypoint navigation. There are two ways our drones can do this. We have created a program that can be run using the test command in off-board mode that allows the drone to subscribe to pose array messages sent by the user and move to specified waypoints in the position flight mode. We also have a second program that can be run by the test command that programs the drone to fly to predetermined waypoints given by a series of pose messages. We chose to send waypoints via pose messages because the waypoints can be changed easily and it is easy to determine the exact desired location. We chose to reduce the max velocity of the drone since there is a trade-off between the speed and accuracy for waypoint navigation, and we chose to prioritize the accuracy of waypoint navigation over the speed. Our drones are extremely accurate and they experience very little overshoot when navigating towards waypoints. In the top video, we have a simulation and visualization we use for waypoint navigation. You can see that the drone hits all the waypoints marked by the red RViz markers before landing. The waypoint the drone is currently targeting is represented by a green RViz marker. The drone's trajectory is shown by the green line. In the bottom video, you can see the waypoint navigation algorithm being performed on the drone.
For Challenge 4, our drone is capable of waypoint navigation with static obstacles on the map. The process can be seen in the video to the right. The red and green cubes represent the location of a red or green obstacle from the drone's frame. Our approach follows the next 4 steps. We use OpenCV to segment the obstacles based on HSV thresholding to create a binary mask for detection. We use a stereo camera to triangulate an accurate estimation of the obstacle's location in reference to the drone. We can use the detected obstacles to create an occupancy mapping of the environment to improve the drone's ability to plan a collision-free path. The main drawbacks of this approach is that the stereo depth mapping is inherently noisy due to only being passive compared to typical depth cameras. This can be mitigated with advanced processing of the depth map. Not much is known about Challenge 5 and 6, but the current plan is to use YOLO V5 as the CNN for object detection for whatever the challenge may entail. As well as we're planning to use a finite state machine for intelligent decision making so that the drone can operate efficiently and effectively within the environment.
Our team consists of talented individuals with many different technical skill sets and experiences, including with drones, spanning from ROS and hardware to simulation and computer vision. Our team highly values safety and testing. Through strategic, comprehensive design verification, we aim to identify problems through simulation and minimize hardware failures. Lastly, our team's strong communication and teamwork skills allows our team to come together and work together to achieve a common goal.
Oh, stop. Oh.